van de heer. Ja, van. So, thank you. Yes, so we have seen how, a method how to estimate the finite difference schemes in when the finite differences are considered only in the space variable. And now we go further, and I have already formulated last time this result, that if we have more smoothness, then the finite difference approximation can be written in a kind of Taylor form on the grid in the space variable and in the time variable on the whole T, such that the u1, uk are functions given on the grid and in time, in the time variable from 0 to capital T, independent of age. This is important, and the remainder term is of order k plus 1, where k is a fixed integer here, and RH here is a bounded.
Additional question. Your series starts from h squared.
Thank you. What I'm writing is a kind of strange thing. Yes, started from one, I don't know, that remained there when I wanted to write without the summation. Started and then I forgot. Thank you, Michel. So this is what I wanted to write. Well, how to get this? So this is the assumption for the smoothness on the coefficients. You remember A1 is the assumption that the coefficients are continuously differentiable in x up to order m. So m now should be like this, and here L should be greater than half of the dimension. This comes from the embedding, which we have already learned. Right, the A2 is the assumption on the free terms. So you know that means now that, or that means that in the m norm, Wm norm, the square should be integrable in time, and A3 is the stochastic parabolicity condition. Okay, so this is what we want to prove. I remind you that the equation we have studied so far is this one. You probably know what is LH, MH, I don't write now. So what is the idea of the proof? So because this is a Taylor expansion, it is natural that we would like to take then the derivative in h of the approximation UH, right? But it is a difficult task. In what sense we could get it, and the idea is that we do not show that these derivatives in h exist in some suitable sense, but we guess what these should be, and then we use them in the expansion. That we will consider UH minus the part so far, so the Taylor polynomial, and then the rest we estimate. So how to guess it? The guess is that the solution, the UN should be the derivative in some sense of UH, right? So we take the derivative n times of the equation, and what we got from there, we want to first we take 1 second, third, and so on until in fact k. We want to have this until k. So we have a system of then when we take formally the derivatives, we have a system of finite we take the derivative with respect to h, but at 0. I'm always forgetting to say, when we take the derivative with respect to h formally, then we should take it at 0. Yes, okay, when we do that, we will have a system of SPDs, and the thing is that we have to solve that, and then from the solutions we get these functions here, and then we, as I told you, we subtract the right hand side, this part, from UH, and then the rest we want to estimate. Okay, so this is the plan, but first then we need to start with understanding what we get if we take the derivative of this. Remember that we consider again this one as a finite difference scheme, not just on the grid, but on the whole space. Okay, now in order to justify the derivation we want to do, let us first give a lemma, but before, okay, the lemma. So first define M, let's say here N, that is the number of derivatives on the operator H, and on phi, so we define this at X, and also at a fixed t, as the derivative in H of order n phi x. Similarly for L, oops, what I'm saying, derivative, sorry, derivative of H, M, H, and there is also a row in that case here. We also write the row on phi, and similarly for L, Ln means acting on phi, the derivative in H of order n and H rho phi. This first we define for C0 infinity functions.
So this is derivative, not descriptive.
This is derivative and not discrete derivative. Yes. So let us see. Okay, but the statement first. So we have this. Then we claim. Then oops. Obviously, this is L. Yes, this is L. Here. Okay, L of H. Then we claim that these operators M, N are well-defined linear operators such that the norm of Mn on phi in the WL is less than or equal than a constant times and phi n plus L plus 1, and then similarly for L less than or equal than n phi n plus L plus 2. Moreover, so this is first thing. Second thing, that
what is rho? M rho What is
Yeah. All right, the rho is the coordinate, and again, my bad habit that I forget to write the UH, which is, and here the rho also, and here the rho also, and summation. So this is a finite dimensional linear process, D1 dimensional, and so here we have a vector, and this operator is also a vector. So sometimes I do write, sometimes I don't write the rho there.
Your operators, do you evaluate h equals 0 or just derivative?
Yeah, thank you very much. So in fact, in the definition, I evaluate at h equals 0, and also here at h equals 0.
Is H, like, how H and rho are related?
No, wait, the rho is just
Summation 5.
rho.
I thought that
Okay.
was small.
No,
Not even 6.
right, and here then h5 minus the sum from 0 to k hj. So I write down the Taylor expansion for the L, then this is less than or equal than h, k plus 1, phi, L plus k plus 2 norm. Right, k, I should have that here. I take k, a fixed number, integer. L is also a fixed integer, and here that, and then the L h phi, the same thing. L plus k plus 3. In fact, here we have to, in order to, oops, I forget the constants, and we have to assume, because L is in the LH is a divergence form, unfortunately we should require from the derivative the things here as well. Here one should have so here provided that A1 holds with M greater than or equal and L plus K plus 2 is enough. Now, I hope I have written down properly, but if not, that it will turn out when I try to give the hint of the proof. So, let us just this MH, we remember, is that the B, or here with the rho, BI rho delta HI summation over I from 1 to D plus the B0 rho times the phi, so phi here. So no dependence on H here, so the derivative exists and 0. So we are interested in this term and see the derivatives in H. B does not depend on H either, so the only thing we should understand here is the delta HI phi and its derivative. Now this one can be written as from 0 to 1, the derivative in the direction of EI of phi at x plus h theta EI d theta. This either we can see it from Taylor formula, or the usual thing is that, or the fundamental theorem of analysis that recall that the that delta hi phi is 1 over h times phi x plus h ei minus phi of x. So this one is a function of h, or oh, sorry, it's better if I write it like this, that let us consider the g theta of theta, the phi x plus h theta times ai. Then what is written here is the difference so what we have is that this equals the t at 1, g at 1 minus g at 0 divided by. So this difference is the derivative of 1 over h, the derivative of the g, the theta, and when we write it, then derivative of g in theta means the derivative in the direction of ei times the h divided by. So anyway, we get this
Maybe just
formula.
want to emphasize that the g is not the same g before.
Ah yes, this g is not the same g, so this g is just the g bar. And here prime means the derivative. All right, so we can see that if phi is differentiable, then this operator is differentiable, and so the h to the n of this delta hi phi equals, so phi at the moment is c0 infinity function, so we take the derivative and n times in h, so that means here we have di for the n plus 1 times phi x plus h theta ei, the theta times theta to the power n d theta. And we see that in fact for each h on a 0, 1 or minus 1, 1 interval, one can estimate the L2 known uniformly in H from here. But all right, let us see what is this in what is this when we take H equals 0, then we just get this part equals 0 here, so we have the derivative of phi of order n plus 1 in the direction of I, and the theta n should be integrated, so we got 1 over n plus 1, and the derivative, so the of order n plus 1 of phi. So clearly this which is so we see that the operator mn rho phi is acting on C0 infinity functions is just b I rho 1 over n plus 1 d I n plus 1 phi, and right, so summation. So we can easily see that the first estimate is valid, right? If we take the L plus L norm of this sum, then we estimate this by a constant, because these have derivatives, bounded derivatives up to order m. So we can see that this L norm is less than or equal than a constant times phi L plus 1 phi L plus 1 L plus n plus 1, because here we have n plus 1 derivative plus L derivative should be considered, right? So L plus n plus 1 from each term when we do that, so this estimate is valid. Now the other one is a little bit more complicated. The reason is that the LH is in the discrete divergence form, so therefore, so let us have a look at that. So LH has this form, that delta minus HJ AIJ delta HI acting on phi summation over IJ from 1 to D plus the rest. Let us not concentrate on the rest, because that is the easy part. And here there might be different ways, but we can just take the finite difference. So this is finite difference on the product, so we can write it down as a summation over I and j from 1 to D, and Aij delta minus Hj delta Hi phi plus, so we take the discrete derivative of the product, that is, we take the derivative of one term, this is what I have written down, plus the derivative of the other term, but on the shifted, to be precise. So then this is derivative h minus hj on aij and delta, so here this is the derivative, the discrete derivative, so difference, sorry, delta hi, and we shift. So I interchange the shift operator with the finite difference, but that can be done. Okay, we shift minus h in the direction hj with minus haj. We shift the function phi. So this is what we have. So this is the extra term, and then we represent each terms again in integral form, and we can see that it is differentiable, and we can even get exact formula for the Ln in parentheses. So let's see just the first term. So again, this is a constant in h, does not depend on h, so we need to understand the derivative of that one. So first let us represent the h minus delta minus hj, delta hi, phi. Now this can be represented by the same way as I have written down, by the same method. But now first one writes down this. Again, one uses in the same way the delta operation. When we put that together, that means two integrals, and then derivatives on phi in direction j, in direction I, in direction j, and phi, and then x plus, let us call the plus h times, then what we get, theta, let's say theta 1 belongs to this, so theta 1 ei, and then because here we have minus h, therefore here we have the minus theta 2 ej. Right, and d theta 1, d theta 2, this is an integral representation of this operator. And then from here we can see that we can take the derivative similarly. So what we get is that d, when we take dh to n of delta minus hj delta hi phi equals the integral from 0 to 1, from 0 to 1, and you see then what comes out when we use the chain rule is that theta 1 times derivation in direction ei minus theta 2 derivation in direction ej, then this comes out n times, acting on this, so dij phi x plus theta 1 I minus theta 2 ej h, and d theta 1 d theta 2. So we can see that at h equals 0, we have the when h equals 0, then we have that this operator, I can write it only at this integral form. Now, rescue dij phi,
This is theta 1.
and also d theta 1, d theta 2. So at h equals 0, we get this one. Is that okay?
Just notation that the theta 1 di, right?
right now. What is the common?
This one, what does that mean?
The common EI.
So di means the derivation in the direction of each y.
Yes. Okay, that's the
Yeah. If we would like to have a formula without the integrals, then we can do that. So we write this down by binomial formula. We integrate when we take so here when we take h equals 0, then we should integrate only the theta 1, theta 2 integrate out, and then we see that here then at h0 we get an operator of order n plus 2, right? So when we now take the L norm, yes, then that is less than or equal, oh yes, why?
Is it di or theta? EI. Should be EI, right? Theta 1 EI.
Chain rule.
Theta 1 and theta 1 and d e.
EI.
Yeah, d e I, but for short I use just the I index not to write too much, and here dj. Right? So then it is an easy exercise to see that the L norm of this is less than or equal than n times the phi L plus 2 norm. Right? So n plus L plus, again lost the n, yes? N plus 2, the order of operate, if the derivatives, the order of derivatives is n plus 2. I took the L, an extra L, and then plus, so n plus 2 plus n. Right? This is how. One way is to argue quickly to use Minkowski with respect to the L norm, that this one, the L norm can be taken inside of the integration by Minkowski using then for the WL L2 norm, and then what remains is estimated by that norm, and then the integration gives just a constant.
EIG of T is not independent of theta.
Sorry?
EIG T is independent of theta.
Yeah. In fact, I don't need. Yeah. Sorry. Forget, please. That so this is easy immediately. Yeah. Okay. Thank you for paying attention. So yes. So I only showed this part that can be estimated, but by similar method this part as well. So here the shift doesn't make any change. The norm of the function is the same as the norm of the shifted function, right? Here this is estimated by constant times the derivative of a. So one should have an extra derivative to require from a because taking that. So if we calculate properly, I hope I did that in this case well, then these estimates can be obtained. And that means that we can extend these operators to be a well-defined bounded operators from here from Wn plus L plus 1 into WL, and similarly here. So we have well-defined operators, bounded operators between the suitable Sobolev spaces when we write Mn and Ln. Now the last one, or the second, so this one is just the use of Taylor formula. So second maybe converts upon the.
You need
So here, yes, yes, that's right. If I want now, so you mean in the second? Yes, it's better really to use the second in not in this norm as I have written down. So maybe I have to write down again and to write it also in in this. Oh no. I think that's fine. That will be fine for me. That's enough. I don't need anything more. That's fine as it is written. Now how to get this one? So the second. So here one uses Taylor formula. Again, first phi is a C0 infinity function. So here then we have some function of h. We know its representation. Let's say let us deal with, in fact, with this first. So let us, which means again that if we would like to understand this, it is enough to consider only the delta hi phi situation, and we know this is integral from 0 to 1, the di phi x plus h theta d theta. So this is a function. It's better not to. Okay, I use then g, but this is again a different g of h function, and then we write down Taylor formula for it. So g of h equals the sum n from 0 to k h to n over n factorial times derivative of g n times at 0 plus, and then in the integral form the remainder term is good to written down in the integral form. So from 0 to 1 and if 0 to 1, instead of writing from 0 to h, then I write 1 minus theta to the n, and then g, the n plus 1 derivative, that means the derivative of g of order n plus 1, h, oh, I have k at the, oops, I lost, sorry, and that's, for here only k, here k plus 1, h theta d theta, and here h k plus 1 over k factorial. So this is just the usual integral. It is written in the integral term, but not from 0 to h, which one usually does, but I took out one more h in order to get here the hk plus 1 over k factorial. So this is the formula. Now, when we subtract, then so this equals what is written down here. So we see that if we have, instead of mh, just this operation, so the constant doesn't, so that we have a coefficient which does not depend on h, so we can easily take that into account. So in fact it's enough, I think, to see that the L norm, yes, the L norm of this one, L norm of this one is less than or, okay, this is just the same as the L norm of this one, right? And now, okay, here I use, this is less than or equal than the hk plus 1 over k factorial times integral from 0 to 1 minus theta k, and then g k plus 1 derivative h theta L norm and d theta. Now we have seen the derivative up toward the k plus 1 of the g function. We have already considered, and we have seen that that is in fact when h equals 0, but just the same estimate for other uniformly here. So therefore what we get is that this is less than or equal to hk plus 1 times a constant, and so here we have k plus 1 plus L derivative, and plus we know that there is a 1, so we get that it is less than phi, and k plus L plus 2. So I think that I explained this part, not taking account the constant there, but the constant is always there as well, and when you take the derivatives, then you have the same multiplier at the end, you take out that as a constant. So this one is explained. I am not doing now the other one, little bit less writing to get that as well. So let us accept that we have this lemma. Okay, now the proof of the theorem. I don't know what name should be given to this theorem. Maybe this has number 3. I don't know. I give now number 3. So we take the formally the derivative. So remember again, duh equals LHUH plus F dt plus MHUH plus G dwt and with initial condition. If we take formally the derivative, one derivative in h of the equation, so both sides of the equation, then let's say I write this u1 du1 equals then lu1 this disappears plus L1 u derivative in h at 0. So then LH at 0 is the L operator. So this dt plus similarly m m u1 plus m1 u dwt. There is always the rho at m as well, and here and here as well, and the initial condition is 0. So we do not justify any derivations of the equation. We just consider this one, which we formally obtained. This equation is well defined. Yes, L1 is a well defined operator. So to make it more precise, here this is free term, and here we consider these free terms as well. So for us now the u, the solution of the true solution is given, and we want to define the u1, so we define the u1 from this equation, where everything is well defined, the original operators, and this L1 is a well defined operator, and here M1 as well. So to make things easier, let us just consider the case, instead of the general one, consider the case k equals 1, right? Otherwise, if k is 2 and so on, then we take formally the second derivatives and so on, and then we have a system of SPDEs for these u1, uk. But let us not doing the general case, just k equals 1. Right? Okay.
Question.
I just wondering the equation omit h, or
It's partial
did
differential.
you use the first one or original equation?
No, it's partial differential.
Yeah, but
It's partial differential.
So this one now is a partial differential equation. Yes. So we obtain that formally because we think that we guess that the u1 in the expansion must solve the SPDE, which we obtain by taking formal derivatives of the approximation. Right? So from now on, forget a moment that what we have done here, we have this equation. This defines for us u1. Okay, and right, and then what we consider is what we need to prove, right? That the UH, so aim, UH equals U plus H times U1 plus the H square and some R here on the grid But again, we consider this instead, we want to have such an expansion instead of the grid, we want on 0 capital T cross RD. And then, as always, if we have that, then just restriction and having the extra d over half makes it possible to have the embedding of the UH and U1 into little L2 or on the grid. Okay, so how to prove this? As I mentioned, what one does, that one takes the U1 from here and then one considers the UH minus U minus H U1, and the aim is that to show that it's L norm is less than or equal to the constant n times h squared, right? And next step one takes L greater than or to d half, such that then this is true also on the grid when we restrict it onto the grid. And also in supremum, so this is in fact here supremum in T. Here we have the T, that we have this estimate, so this is the aim, right? So we have an equation for the UTH, UT, and also for this one. So then, for the quantity we are, or the function we are interested in, let me denote it by capital R, also depending on T, depending on X, and also depending on H. So let us write down an equation for the capital R. Then d capital R, which is the d of UH minus U minus H U1. Then we can check the following, that this is LH on capital R plus, let us, my notation is, I don't remember my notation, so this, and now maybe I put here F1 dt plus NH R plus G1 dWt, and the R at 0 equals 0. So where the F1 equals the LH U, oops, maybe like, okay, minus L U times H squared plus L times h, sorry, nothing to get h square from yet, LH minus LU minus h times L1U, and that has the h square. Similarly, the G1 is MHU minus MU times H plus the similar expression MH minus M. So here the U minus H M 1 U. Okay, maybe you let us check why that this is really so. For example, for the first one, yes, so let us check here, just that F1, so the new free term is in fact in this form, and similarly this in that form. So when we write this down, this differential, then we have this kind of expression that LH on UH, also the free term, but that disappears. Then we take that minus the L on U, the free term disappears, and then minus H times the LU1, but also there we have the free term minus H L1U. Okay, and instead of that we want to write LH acting on this difference. Yes, R. So LH acting on R, then that means instead of L we have LH here, so we should that give back LH U, then minus LU, then minus H, and maybe first, instead of that we have written LHU1, so we should that add H times LHU1 and minus LU1, and also minus 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 H L1 L1U, minus H L1U. That means here we have then LH minus LU doesn't seem to be the same what I have written down. Where have I lost the H? Must just
There is no equality sign anywhere.
I just
No, but in this box, there is no very. What is equal to what?
yeah, I tried to write it down. So that is here LHR, and then
Wait. You started with the first line.
yeah,
Where does it end?
so
The
the first line is this one, here it ends, and so it equals here. So this one is what the differential equals. So LHUH minus LU minus HLU1, right? And then we also have the minus HL1U, right? When we subtract, so H times and LU1 and also minus HLU1. So that looks correct. When we take the LH, then take out the R, we have to have here the compensate, LH minus L, then on U, here H times LHU1 minus LU1 to compensate, and minus H times LU1. So what we got, this equals that one plus the LH minus LU plus H times the LHU1 minus LU1 minus HLU1. Right. So let me stop here because, oh no, I still have them. I still have them. That's fine. So I got here LHU minus
The second
L.
should be U1.
Sorry?
HU1, I think first time.
Let me check that right. So I am absolutely sure that this must come up, and this as well. Where have I lost this? That this, so the last one comes to here, to the LU and minus H1. So this term I should take together with this one, so minus H times L1 U. That's that. And then what remains plus the LH minus LU1. So that's all right. So please check. I haven't written
U1H.
and here U1H. Thank you. That's the correct way. And so I think I made here the mistake that here I should write the U1. Similarly here, and one gets this. So that is that all right? It's very simple computation. In fact, in k equals 1. So sorry for this difficulty. And then now check that if now we can write that if we want to estimate the R from this equation, then what we know that the supremum RT norm L norm squared expectation plus the integral norm, but we don't need to use that. Oh, by the way, today Professor Kerr no, that I don't want to mention, because that what we are using now is in fact what we have proved. So I don't need to refer. So here we have the discrete equation, right? And for the discrete equation we have the estimate proved, and this is what we are using, that this one plus an integral known where discrete derivatives, but we don't use that, is less than or equal than n times, and the initial value is 0, so that is not important. From 0 to t, the f1 L known squared plus g1 L known squared dt. Here, this is there are the indices rho, but we sum them up. So that means this is less than or equal. And now we know that when we have this difference, then that is less than or equal, so here, then m times expectation t, and for that difference what do we know? That we have the h first, I hope I will remember, so there is one h already here, and from this difference we also get another h, and so u1 t, and what known? L plus 1 plus 2 norm there. So L norm I take, then 1 the derivative gives an additional 1 plus, because of the difference, so an additional 1. So L plus 2 square dt plus
H square.
yes, I want to write that at the end. Sorry. Okay, I kept in mind, but you're right that
The main thing.
yeah. I should have written at the beginning, but I will write at the end. Sorry for that. I try to keep it in. Now here we have again L plus. Sorry. Force for the f. In fact, here we have 2 derivatives plus the difference. So here this is plus 3, and in the other I have plus 2 L plus 2, and now dt, and I multiply by the h squared. Right, and
It's pure U1, right?
No. So this term is just
Что ты не надо показываешь? Не на ту линию показываешь.
yeah,
Okay.
this one. So once again, so here there is one h, then we use the next this one with k equals k equals 1. In fact, for that, with k equals 0, yes, and then we have that L plus 3 norm estimates, and we get an h. So this is why I wrote the L13 norm, and so the h together with that one gives the h squared. Now in this case, we have the k equals 1 situation, so we immediately get the h squared times n, but then with the u norm, and here then also, in fact, am I right with So I use this with phi equals u. So then, and k equals 1, L plus 4. It seems to me, yes, L plus 4, this one, and h. And what we get from this is not worse, a little bit better. So in fact, this is our estimate. So we should then go back and get the estimate for this integral term, and I finish in a minute. Excuse me. And for that we use the estimate for the solution of the SPD, but not in the L2 norm as we have seen today, but in the L plus 3 norm, which can be shown, the estimate, in the same way as and will be shown by Professor Coulomb. So when we use this, the estimate for the derivative of u, so for the equation which is satisfied by u1, and also for the equation, for the original equation, you write down those estimates in the terms of the free terms, original free terms f and g. Then we must get the result I formulated for k equals 1, if I haven't made any mistakes. So thank you for the attention.